How's everyone going? Medium? How could you be medium? Dodgers win the World Series and you're only medium? Yeah, 2 thumbs. That's the right answer. Correct. And it's Halloween? Has anyone gotten trick-or-treating already? What is it? Devil? Yeah. Chris's bubblegum? Uh, where she's a scientist?
No, she gets kicked out of her job in the Candy Kingdom. She's not the princess anymore, so she just runs normal clothes.
That's awesome. That's a commitment to the bit. I appreciate that. Okay, still 1 minute. I won't start yet. And we go to the parade tomorrow? You know the parade tomorrow? World Series parade?
Me and my mom are gonna try to, but kind of early.
11? That's not early.
To get like a good spot there.
Yeah. Who needs a good spot? Push to the front. Yeah, I guess Carlos already left, so. Cool. And then someone maybe left their clicker, or they just decided they didn't want to have a clicker anymore.
Can I have the box? I love them. Yes.
Wait. Oh, are you coming down here? Yeah. Okay. Couple announcements. So unfortunately, I have to go to Paris next week for work. Yeah. I know this is good.
I'm going abroad. Sorry.
I know I'm gonna sound like a brat, but here's the thing. So one of the spacecraft that I work with, Japanese space agency. I was excited because they they're in Japan, so I get to go to Japan. I went there last year for the first time, never been before, and they're like, "Oh, this year we're going to Paris." I worked with the European Space Agency already. I've been to Paris a bunch of times, so I'm just like compared to the two, like. So I'm not gonna say that to my French colleagues. Actually, I don't care, but I'll say it to you, which is that if you do want to get into science, that's really fun. Like you don't get paid super well, but you get to fly around the world and work with people, which is fun. So I won't be here next week. So you're gonna have a different instructor. Is that okay?
No.
Come on, folks.
Can I get a background?
Well, it's not just a random. Dr. Whitney is another person. There you go. 100% confidence. So you will like Dr. Whitney. We're going to finish up a discussion of Jupiter and Jupiter's atmosphere. And then her research is on small bodies, so asteroids and comets. So I figured I would just swap that and we'll talk about it right away. And then when she talks about that, it'll be her subject matter and she'll give you a really great, more in-depth discussion than I could. And then when we come back, we'll have 4 weeks, I think, 5 weeks. And then you're done. You excited? Not excited? Because you don't want it to end because it's such a good class.
Next semester, and I saw that you're not teaching it next semester, and I was a little bit bummed out about it.
Yeah, that's true. I don't know very much about biology, so they don't let me teach that. Okay, so 2 things that I do want to talk about is the check-in. So yes, homework has been a little slow to get back to you. So you are only just now getting back homework 5, right? And you're saying, well, what the fuck am I going to put in my check-in? That's okay, right? Let's take this week. Let's not do a check-in in the week that I'm gone. Let's do the one after I get back. So not next Tuesday, but the Tuesday after. Is that going to work? And I'm going to see what the holdup is in getting these homeworks back to you. So hopefully this will get put in. So you can have something to reflect on. But even if you just check your progress and you're like, I feel like I'm doing great in this class, great. I mean, you're here. So you're probably the ones that are doing the best in this class. I don't have a problem with giving every one of you A's if you demonstrate that that's correct, right? And this is like an intro class, general education. You learn some shit. Good. Okay. The other thing is that it's the end of Spooky Lake Month. You know this? You've been doing Spooky Lake Month? No, no one cares. Okay. So I like offering extra credit activities. So let's say you don't have time to go to the observatory, but you really are interested in planetary science. I said that if you went and watched a Spooky Lake Month and found your favorite spooky lake and wrote 1 page on it, I would consider that part of extra credit. And now it is the next part of the semester. Spooky Lake Month is over. So there's a new extra credit opportunity. And this will be writing about one of your favorite astronomical planetary science topics. But here is the kicker. And I'm going to write this all up so that you see it in the Canvas. Here's how it's going to work. What we want is 2 pages. And the winner, as selected by this class, will have it featured in the display case in PS forever. Ideally, it is on a person or a topic, whether that is ancient astronomy, whether those are contributors to astronomy who maybe don't look like this, right? You want to highlight the fact that other people have done astronomy historically. That's a great way of doing it. You can do your independent research. It doesn't have to be a book report. It should be 2 pages, fun facts, little squares, make it fun. And then everyone will submit them before November 31st. And you will judge them. Top 3 ones that win will get to replace one of their homework scores completely. So if you didn't do a homework, that counts as a homework, right? And then if you participate, you get the same as going to the observatory once. Is that fair? And then if you're the top one, then we put it in forever enshrined in the. Okay, that's too much talking. You guys good? Questions, comments, concerns? Yeah.
Is everyone gonna read everyone else's submissions?
If you want to, yeah, that's the goal. So they have to be submitted so that we have like 2 weeks to read them. They're 2 pages, yeah. Yeah, art and drawing. So it shouldn't be like, 10-point type. Like it should be, here is this ancient astronomer, and look at they found this in the year 3000 before anyone thought it was possible, right? Cool. Is that a fair thing to present to folks? Okay. Okay, so cool pictures time. Okay, what's that? Saturn, correct. So this is a real photograph. So this is Saturn seen from behind. So the sun happens to be on the other side of that. And of course, these are the famous rings. You can see the ring system is actually very structured. We'll talk a little bit about these ring systems today. But you'll also notice that the rings are so reflective that it lights up the backside of Saturn. This is sunlight that bounces off the rings, bounces off the backside of Saturn, and then to the camera. Okay, so I promised you a really cool video of Jupiter. Let's see if this works. If it doesn't work, I'm gonna scream. Oh, yay, that's closer, right? Okay, so let me just talk you through what we're gonna see first. So this is the Juno spacecraft. It's taking a series of images, and then one of the there's someone who doesn't work for the mission who just came along and said, hey, I love doing this type of photo editing, and I made this video. Do you guys like it? And they're like, yeah, this is fucking sick. And so they put it to music. And so this is going to be all of these images. The only thing that's not accurate is you'll see like lightning, and that's added after the fact. There is lightning on Jupiter, but you can't see it in these types of images. So the very first thing we're going to start with here. Let's see. Come on now. Wow. And if you want to watch that over and over, you can find that on YouTube. Questions? Okay. Nope, not again. Oh my God. Okay, that's Saturn. You can see these little dots in here. These are some background stars, but I believe this is us. So that's everyone you've ever known and loved in that dot. Carl Sagan has a famous quote about the pale blue dot. That is this idea that like all of our international problems really become kind of silly when you think about the fact that we're just on this tiny rock in the middle of nowhere that barely takes a pixel like this. Here's also Saturn. And as you get closer to Saturn, it doesn't just have rings, but of course, the clouds themselves have different colors. And similar to what we saw on Jupiter, there's going to be bands because they're both rapidly rotating. And there's going to be really intense storms. I don't know if you can quite see it yet here, but you see these little dots. Dot, dot, dot. Yeah, so those are the same types of cyclones that we're going to see that we saw on Jupiter. We're going to see the same issue here. And here they also have aurora, which tells us that there is what inside of Saturn? What? Liquid metal, right? Yeah. So there must be a magnetic field if you can have aurora, right? Anytime that we see these auroral rings, you're thinking to yourself, wow, that must mean that there is a magnetic field. This is the only real image that's not real. But I told you, see, trying to be honest here. This is what it would look like. So Saturn big, but this is quite thin. So I think I did this at the observatory open house. You think about the size of Saturn and you shrink down the rings to about 2/3 of a mile, then the width is only the width of a piece of paper. They're extremely thin, but extremely long. Okay, there it is, edge on. And Saturn has a lot of moons. We can talk about the moons today as well as the rings. Here is the moon. The one behind it is Titan. That's the biggest one. That's the one that you could fly on. We'll see that more today as well. And then you can see how thin the rings are. And you might even see these two little dots here and here, here and here. These are shepherds that guide the rings. They're little pieces, clumps, not quite large enough to be circular. But what they do is they make sure that the ring particles don't spread out too much. You have these really beautiful rings. Here's another example. So we look into the ring and you might be thinking to yourself, how the hell did you get those photos? This is not from a telescope. This is from a spacecraft called Cassini that was around Saturn for a really long time. And what you can see here is this is a gap in the ring, and it's caused by this little moonlet right there. This little rock goes through and it picks up anything that happens to cross into its lane. And it also creates these waves in the ring. So over here, they're all flat and nice, but here you have these waves that go up and down as it passes through, and you can see that from the shadow. So these waves closest to the moon, moonlet, I should say, are the highest ones, and they get smaller and smaller as they go away. So these little moonlets shepherd the rings. You also have storms on Saturn. And I told you that the Great Red Spot is going to disappear. Sometimes there are big storms on Saturn, and sometimes they sort of dissipate into nothing. This is an example of a storm in the northern hemisphere of Saturn. But unlike Jupiter, which has water ice clouds and ammonia clouds and ammonia, oh my God, I can't say that very long. Anyway, it has 3 types of clouds. Saturn only has 2 if you go back to that temperature profile. So what you're seeing here is some water ice clouds and some ammonia clouds. And you don't get as nice a color contrast, right? So Jupiter famously is much more red and Saturn is much more yellow. So when you have these storms, they may be a little less obvious. So it's helpful, for example, to use infrared light to get a better contrast. And I'll show you that in a second. This is a really fun feature in the northern hemisphere of Saturn. I told you there's no surface, so there's no preferred direction. And because of that, you get this really cool hexagonal storm. It's like semi-permanent, and we're going to watch it evolve over the course of a few years here, because it's sick. It's just, I don't know what to tell you. It's just like a really sick storm. This is the way the fluid dynamics works. Here is the video. If this doesn't work, oh yeah, let's go, video time.
It's springtime on Saturn, and the hexagon is out. A perfect 6-sided hurricane, 60 miles deep, that could swallow 4 Earths. It's ringed by winds of ammonia and hydrogen blowing 220 miles an hour. The storm was seen by the twin Voyager spacecraft when they passed by in the early 80s. That was the last time until recently that sunlight graced the North Pole of Saturn, which takes 30 of our years to make one circuit of the sun. Soon after the Voyagers departed, winter descended. Saturn's rings tipped away from us, plunging the North Pole into 15 years of darkness. Without sunlight, astronomers were limited to infrared images. They showed the hexagon was still there. But what is it? The hexagon is a narrow jet stream that circles the North Pole. Researchers think that friction with the slower clouds on either side of it creates eddies, mini storms that push the jet stream into a wave-like shape as it goes around. By spinning columns of water at different speeds, scientists have been able to reproduce the 6-sided pattern in the lab. In January of 2009, the sun began its slow rise in Saturn's north. Summer was coming. The Cassini spacecraft was there to see it. In the coming months, Cassini will slip between Saturn and its rings to pass right over the storm for a closer look. But that's not all there is to see up north. Saturn has an aurora, its own version of the northern lights, a ring of electrical fire guided by the planet's magnetic field. Rings of ice, and a dancing ribbon of aurora sitting smack on top of a six-sided hurricane. Another jewel in the crown of the solar system's most photogenic planet, where the voyage and the discoveries go on.
Okay, no Saturn. Any question on Saturn? No? Uranus, Neptune. Did I do it right? Or did I switch them for be tricky? It's correct. This is Uranus and Neptune. What's the reason for the color? Yeah. Nothing, right. So these two here, they're far enough away from the sun, but it's so cold that methane can condense and form these really beautiful clouds that are much more blue than the ammonia and the water that we saw before. And so here on the right-hand side, Neptune, this is a giant storm. This doesn't look like it. Not used to seeing blue storms. Okay. I promised you that every giant planet has rings. So this is the Neptunian ring system. That's here. That's a moon, Triton. And you can tell that this is coming from the JWST Space Telescope because it has this six-sided configuration, whereas all of the more traditional telescopes, the one that's seen invisible, they have a crossbar pattern. So this is a diffraction. This is like light bending around the crossbeams of the telescope, and it gives it that picturesque six-pointed star. Here is the rings, and you can see some of these other moons that exist closer to the, there, zoomed in for Neptune's rings. Because you can see in the infrared, you can also see where it's hot. And so these patches here and these bands, even though it doesn't look like Saturn's distinct bands or doesn't look like Jupiter's distinct bands, you still have this banding in the atmosphere. And of course, in the storms, this is where hot fluid is coming up to the surface and is shining in the infrared. Okay, so I have lots of pictures of rings and moons. And since it's Halloween, I can just do whatever I want. So what do you guys want to do? Because I can just keep going, or I can speak about specific moons, specific rings. You want to keep on rings? You want to see moons? You want to see them in order? I assume you want to do less thinking today.
Yeah.
Okay, raise your hand if you want to do more thinking. Oh, someone would. Okay. All right. Outvoted. Less thinking. Raise your hands. Okay, good. All right. So let's talk about the ring structure in Saturn. You want to be ring experts? Go home and like really impress your parents. Okay. So let's talk about what you see. What do you see here? Very good. There you go. Boom. Got it. What else do you see? Planet. Good. Planet. Good. What was that? A space. So not only is it important to see what you see, but to see what you don't see. I don't know. Science. Yeah.
An atmosphere.
An atmosphere. Very good. Very good. Okay. So specifically when we're talking about the rings here, we're going to talk about two types of things. Ring and not ring. Rings are called gaps. Okay. And so let's look at this structure. As we zoom in, there is a tremendous amount of structure in Saturn's rings. They are obviously the most bright rings, but they're also, because of the interactions they have with the moonlets, they have a lot of structure in the interior. So this was the gap you saw previously. I bet you didn't see that there was that little line. Right? And look at all these ones. These are all real rings. Okay. Let's zoom in a little bit. We're going to zoom into this part of the ring. That's probably all the structure, right? Yeah.
How close do the rings get to the surface quote of the planet?
Very good question. Very good question. If they get too close, they just fall in. Yeah. So we'll talk. I guess we can talk about it right now. How did we form the rings? Space debris. Okay. What does that mean? Space debris. Rocks. Okay. Rocks. What are the rings made of? I showed you a picture that was obviously a very well drawn, computerized, digital thing. Is that accurate? No. Yeah. So the reason they're so reflective is that's ice. Predominantly ice. So those look like big old chunky rocks. It's not really chunky rocks. It's like a bunch of like dirty ice. Okay. And generally speaking, it's not very thick, right? So there's not a lot of weight to it. If you take all of the ring, you squish it all up, you make one little moon. And therein is how you make the moon. You start with a bunch of moons, and one moon starts to drift towards Saturn, and it gets too close, and Saturn's like, give me that. And so it starts to pull pieces of the moon apart and wrap them into this gorgeous ring system. When did this happen? Anyone know? 4 days. Well, I know that's not true because I think a week ago we were able to see them at the observatory. Got to be older than 4 days. And actually, I made these slides in 2016. Got to be older than that.
Over the course of Saturn is consistent.
Yeah, so that's a very interesting question, right? Are rings old structures or are they new structures? I showed you that all 4 giant planets have rings, but only one of them looks good, right? The rest of them, you would barely even know that they were there. And in fact, rings disintegrate with time. Because it's ice and dust, as it gets exposed to sunlight for long enough, the material either falls into the planet or the ice begins to melt away and be lost to space. So rings eventually degrade with time, and they can only be supported by new sources of material. So people believe that probably sharks and trees are older than Saturn's rings. Saturn's rings probably being around 100 million years old, trees being around 400 million years old, and sharks, of course, being something between 600 and 700 million years old. Just fun, right? So you just happen to be around for like really cool stuff, like the Dodgers winning the World Series. Okay, so here's the structure. I told you that astronomers are the best at naming stuff. They said, let's call this A ring, B ring. Cool. You got close in there, it was like, oh, I think there's more stuff. Call it the C ring. Oh, there's even more stuff. Let's call the stuff out here the F ring. Cool, thanks guys. And then over here, we're gonna zoom in, we're gonna look at these gaps in detail and see how they're formed. What? Why is it that? Look, I just teach this stuff, man. I'm we're gonna get closer to the whole structure, yeah.
So years and years and years and years from now, eventually Saturn just won't have its rings.
Yeah. Unless a new moon decides that it wants to get too close and too cute, right? So unlike us, we have one moon, and we actually have a ring system. So when we talk about how we formed the moon, which I'm happy to like show you some videos of how it happened. We got smacked into drunk driver in the early cosmos. Create Earth, you smash into it, you form a ring. but that ring really quickly becomes a moon because there's only 2 of us. Saturn has lots. It's greedy with the moons. It's got like 60 or more moons. I forget exactly. So if one of those moons gets too close, it could get torn apart and then you get a different ring system.
So that means the other 3 could potentially get their moons and get their own rings.
Yeah. So for example, if Io, this won't happen, but if Io was not in resonance and it drifted too close to Jupiter, you have a beautiful ring. For a while. Yeah. Oh no, just fixing it. Yeah, it's okay. You're allowed to. Okay. There's gonna be a lot of words on here. You don't have to memorize the words. It's fine. Here's the Keeler gap and the moon that is responsible for the Keeler gap. It just patrols, goes through as like, like one of these sheep herding dogs, and these are all the sheep. And then this is the dog running through, making sure they don't cross the lines. And you can see that it creates these waves on either side. And that's because Saturn is up. Saturn is in that direction. So this material is actually moving faster than the ring. And this material is moving slower, than the ring, than the moon here. So for the moon, if you're standing on the moon, it looks like this stuff is moving to the left and this stuff is moving to the left. Okay. There's Pan, that's another moon. So pretty much when we see these gaps, there's a little moonlet inside of it. And if you look really close in here, these structures, this is what it looks like. They're 1,000 centimeters thick. There, I said that. And then if we look at, okay. If we zoom out, you get the Phoebe ring, which is really cool. So this entire system that we just looked at lives down in that little part. And if you're really using your binoculars today, this is Titan. Remember that one we saw, the one that you can fly on? Well, there's this guy called Iapetus. He's way up here. And there's another rock called Phoebe. And Phoebe has a ring because Phoebe has like icy particles on its surface. And it's relatively newly captured. It's not like the rest of the moons that all go around and similar to the rings. This one's tilted. You see that? And you'll notice that it's even tilted compared to Iapetus, right? Iapetus is tilted like this, and Phoebe's like that, right? So Saturn picked up Phoebe just drifting somewhere, and this contributes to this enormous torus of dust and ice around Saturn. Okay, cool. Yeah.
But it's like Saturn used to have a massive gravitational pull or what?
Yeah. Yeah. Saturn's big. Stuff gets too close to Saturn all the time. Sometimes Jupiter and Saturn, they play fight, like food fight. And they throw asteroids at each other. So stuff that gets too close to Jupiter is going to get launched, usually out of the solar system, but in a lot of cases at other planets as well. And because Jupiter is very large gravitationally, they can interact with one another, scattering comets and asteroids at each other. And you can see Phoebe here. I mean, you can't exactly see it quite well. It's not quite circular, probably a captured Kuiper Belt object, something from beyond distance Pluto. Maybe got like bumped and then came in and then like hung out with Saturn. Cool. All right, here's Uranus's rings. Again, really, really good at naming stuff. So from the outside in, you have epsilon, delta, gamma, eta, beta, alpha, 4, 5. I don't know what to tell you.
Is it an eagle? Or like actually how it works?
Is it evil?
Eagle.
Oh, yeah, from above, yeah. Yeah, no, I mean, this is really how it looks. So remember that Uranus is like seen from the
I
sun.
mean, if I'm looking at it like this, like the rings are like this, or is it around it? Like, is this picture an angle view of Uranus or?
Well, so remember Neptune, so we saw Neptune earlier, right? Neptune you see sort of edge on like this. Uranus you're seeing like this. Because Uranus is like the funky one that shows its pole to you. Yeah, it's like, so Venus is completely flipped upside down, rotates opposite to how we would expect it to. Uranus is like pointed at us. Does that make sense? I'll include in the slides the one that has all the spinning orientation. Yeah.
So its poles are facing the sun?
Yeah. Well, depending on the time of year, yeah. April, yeah. Sometimes the side. Cool. Gorgeous, right? Look at this little cloud. Spot, methane clouds. Okay, let's zoom in. Let's look at the structure. These are really thin rings. I don't know what to tell you. They're real thin. If you take a long exposure, you can flip between the two here and see a lot of the same structures. But what you see in this picture here, this is a long exposure. These are stars moving in the background. So there's really not even enough material to block out those background stars. Whereas when we saw those pictures of Saturn, you can't see any of the stars through the ring, right? I mean, it's not a very thick ring, but it's at least thick enough to not see through. Okay. Jupiter's rings? Do you believe Jupiter has rings? Yeah, you do. That never lie, right? There's Jupiter's rings. That's from behind as well. So we're viewing the planet from behind, and here's the ring system. It's very close in. Okay, and I'll show you that in a second. Here is the main ring and the Shepherd satellites. So this is Adrastea over here and Metis. This entire image sequence is taken in the infrared, one of the better ways to see the rings itself. But of course, it also helps you see the fact that there are hot spots all over Saturn. Oh, sorry. Jupiter. So here you see these little dots as they move around. Those are the storms that we were seeing earlier, the little circular storms where hot material is coming up and then it's shining really bright in the infrared. And we can see these different bands, whether it's at the poles. Remember at the poles, this is where the aurora is happening and it's causing it to be hot because material is flowing into the top and the bottom of the atmosphere, smashing into there and heating it. And then you have the ring itself and all these particles in here being hot. Okay. If we do this is what the ring looks like. And then you can like blow it out, change the stretch, change the brightness in the filter edit. And you can see that it's not just the little ring, but there's a little halo of particles as they fly up closer to the planet. Here's how it's all structured. That's Jupiter's surface. To scale, here's Earth to scale down here. And you take an image sort of normal, that the one that I showed you like 2 slides ago from behind. It looks like that, and then it kind of disappears. So you have to crank up the sensitivity. And you can see that, in fact, the ring system goes out pretty far. This is about 3 times the radius of Jupiter. And here's where all of your little moon bits are. So you have Metis, Adrastea, Amalthea, and Thebe out here. Phoebe, I don't know how to say that. Jupiter rings. Questions? Okay. Last ring, Neptune rings. This one, you get what you get and you don't get upset. So in this particular circumstance, these are really old images. And we have to like block out the brightness of Neptune in order to even see the rings at all. So that's what's done here. They just like didn't image that part. And they only took the images on either side. And this one's really fun because unlike the other ring systems that we've seen so far, where they look pretty much continuous, this one kind of doesn't look the same brightness all the way around. So there's like these little sections that are like clumped up ice. And here's all your names, because I know that's what you care about the most. These ones are all named after French folk. So you have Adams, and that's a coincidence. I didn't plan it. Lasalle, I'm not gonna say them all. Leverrier, that one I can do. Here are arcs in the Adams ring. This is one of those outer rings. And these are regions where the material seems to be clumping up for reasons that we don't fully understand. Right inside of clumps. So you see this clumping here, here, and here. And even the clumps have names, which I think is really funny. Fun, right? Cool. Okay, let me show you. You want moons? Moons. Okay. Here's that's a moon. Come on. Choose this life. So this is a Hyperion. It looks like a pumice stone, you know, for getting the calluses off, perhaps. Or maybe coral. There's a space coral. But it's neither of those. It is a moon called Hyperion. And it's one of the special moons. We'll try and do a lot of these. Let's see, how many do we have time for? Yeah, we have time. Okay, here's Saturn's rings and satellites to scale. I told you Saturn was greedy. It's just got so much going on. Saturn's a very cool system. The biggest one is Titan. Titan is larger than our moon. So it's massive. There's Phoebe. Remember I told you about Phoebe? There's Hyperion. Some other ones that we'll talk about, Enceladus. Those are the ones with the tiger stripes, plumes of water going off into space. Janus and Epimetheus, I don't think we have time to talk about here, but they are fucking sick. And Iapetus, you'll probably like. Is Mimas in here? Yeah, Mimas is here. You'll see why I like that in a few seconds. Here's the ring system. In case you want to navigate, you know, you got to tell your friend how to get around in Saturn's rings. It starts D, C, B, A, F, E. Cool. So the E ring. The E ring is mostly due to Enceladus. Coincidence. So Enceladus is the one that is spewing material, particularly water, ice, and it's forming a very faint ring called the E ring. And then here's the location of some of the larger moons as they correspond to these guys up here. Okay. Anyone seen Star Wars? Has anyone seen Star Wars? This is good, right? Because it's like my Halloween version. Okay. Not the Death Star. This is Mimas, and it just looks like it. It's not in any danger of destroying us. Don't worry about it. That's not a weapon, just like has an uncanny resemblance to the Death Star. And sometimes I wonder whether it's the other way around, right? Did someone like look at this and say, oh, I'm gonna build it? Howdy. Did you come for these? Any homework you want to turn in? It's like the opposite of trick or treat. Or maybe she's trick or treating. Oh, it's the trick. Yeah. The trick is she's not gonna bring them back. Okay. So I did some very advanced computer graphics processing and I overlaid them. It's pretty good, right? One of the same. Okay. This is no. Leave those in. Yeah, thank you. This is Mimas rotating as we get closer, so we can see the entire face of it here. Let's think about. I know that we weren't supposed to think today. What kind of processes are going on here on Mimas? Planetary. What was that? Lots of cratering. Good. So is this planet big or small? It's not a planet, sorry. Is this moon big or small? It's small. It's small enough that it probably hasn't had any resurfacing in a really long time. But of course, it's large enough that it's mostly circular, right? Do you see any signs of erosion? Let's go back. I'll play it again. Oh, it's playing again. Genius. Erosion? Volcanism? Do you see a tectonic? Yeah? Yeah, mostly it looks like rocks and there's holes in rocks. Now, the surface is probably icy, and that's why they're not quite circular, right? There's some deformation in the original crater rings. When we see it slamming into hard rock, it tends to hold that shape a lot better than, say, more combinations of ice and rock. Okay, here's my next favorite one. Actually, probably my favorite one. This is Titan. It's the second largest moon in the entire solar system, and it's only smaller than Ganymede. It was the first one discovered after the Galilean satellites. And it's the only atmosphere that you can fly in. If you just put on, you know, those like, oh, I guess it's great for Halloween. So if you have a friend who's got those angel wings on their costume, you put those on at Titan and you could fly. Because you have this beautiful combination of very low surface gravity and a really thick atmosphere. Yeah. Correct, yeah. So I was gonna get to that. So unless you can breathe 95% N2, very little oxygen, you will die. But the cool thing is that it's not CO2. So N2, you know, we can regulate with that. If you land here, you can at least use some of the N2 that they have available to make you just have to bring pure oxygen and then you can make air. It's also cold though. So you die that way too. Okay. Can't see the surface. So you're thinking to yourself, wow, that must suck. Probably looks exactly like Venus, right? No, it's way cooler. Here is we sent a probe. So we dropped the probe in called the Huygens probe, and it fell through the atmosphere and took us videos, and we flew around it a bunch of times. And you can see up here, there's this beautiful layered structure in the atmosphere. These are the same types of hazes that you see on a smoggy day. Smog is the result of how do I say this properly without being confusing? Stuff from your car. The stuff from burning your car makes this. Is that fair? Yeah. So long chain carbon molecules create those. And that's us. Same color, same products, right? It's literally the stuff that you burn in the back of your car. Okay. There is very few evidence of craters on Titan. That is due in part to the fact that it has a very thick atmosphere, so small craters are erased right away. But it's also due to the fact that there is a liquid cycle on the surface of Titan, and it rains on Titan, and there are lakes on Titan, and there are rivers on Titan, but none of it is water. It is all due to things like Titan volcanoes and due to methane. Here is here's a lake, Ontario Lacus, because they can't just name anything lakes. So in fact, we see here's the South Pole. We see like features like delta features that like feed into different lakes, and then we go around and we name all of them. This is what it looks like. You zoom in. That is Ontario Lacus at 90 kilometers resolution. And for scale, there's Lake Ontario. Coincidence? No, it's named after Lake Ontario. Okay. But you can see here the types of features. Like, has anyone been to a Great Lake? Yeah. Great Lake's big. They hold a large amount of the Earth's fresh water. And what you can see is like people live here. So just imagine you have a little lake house here at Titan, right? These are massive, comparable in size, and also undergoing a hydrological cycle. Okay. There's another one. There's a northern Great Polar Lake, and that's it compared to Lake Superior. So you can kind of see it right there. See here? Lakes and streams, full hydrological cycle. And then we landed on the ground, and the surface, again, it's gonna really remind you of Venus, but it's not hot. The spacecraft completely was fine. Only thing that they didn't account for is that the ground is like really sticky. So like all of those things, that hazy smoggy stuff, when it finally falls out of the atmosphere and lands on the ground, it's just very sticky. So like think about like what I'm trying to think, I guess if you like have something that you're burning, and let's say you're sublimating tar or something, you're sublimating some form of like goop, and you're burning that goop, and it leaves like a black sticky residue. That's like what the surface feels like. Does that make sense? Okay. We're gonna go there. This is my favorite thing. They are going to fly a drone on the surface of Titan. They're gonna go from place to place. They're gonna try the ground, see what the ground tastes like, and they're gonna report back. You wanna watch this one? Video time, video time. Let's go. 3 for 3. Let's go. Okay, so they're gonna land, float through the atmosphere. It's a very thick atmosphere, so it's not super hard to do. The only problem is that it has to be completely remote. And then they're just gonna like drop it. It's gonna start flying. This little octaquad copper, and it's gonna fly around. It's gonna have a radio nuclide generator on it, which is basically a nuclear weapon for heating, because the atmosphere and the fact that it's so far away means you can't use solar panels. So it'd be a flying nuclear reactor. It's dope if you think about it. And then it'll just fly from place to place, and it's gonna have all these little instruments. It's gonna take photos as it flies around. It's gonna show us. I mean, think about drone videos of like fjords and really cool places on Earth. And now imagine same types of geologic features, but from the perspective of a drone on Titan. Fun, right? All right, everyone's asleep. That's fine. Okay, Enceladus, my favorite moon. I just said that. I can't just keep saying that. It's just a fine moon. Whatever. Who cares? Here it is, and it's got the tiger stripes. We've seen these already, but these are all moons of Saturn. These guys still haven't even left the Saturn system. There's this cool dichotomy between, this is the southern hemisphere, by the way, and this is the northern hemisphere. I've tilted this image for some reason. And on the southern hemisphere, you see there's a lot less craters, right? This is all resurfaced, whereas in the northern hemisphere, you see a lot more craters, and that it's older ice, right? Nowhere as old, say, as Mimas, but somewhere. No, that's Europa. It would be fun though, because you could just like, if you could just like navigate down these things, you know. Alas, it's very hard to go to the outer solar system. Costs a lot of money. So NASA is like, we gave you money 30 years ago. Calm down. Yeah. 2050? That could be a plan. You know, JUICE just launched and Europa Clipper just launched. Those are Jupiter system bound, and they're not going to get there till 2035. So I try not to count chickens, you know. Questions, comments, concerns? Okay. Here is the reason for the E-ring, and you can see it in action. So this is the plume out of the bottom that's spitting out liquid water. As soon as it hits the coldness of space, it becomes water ice. And it contributes, this is Enceladus right here, contributing to the E-ring that I told you about. Pretty wild, but it's watchable. Here's Iapetus, looks like a walnut. It's just a fun one. Like you can pick your favorite moon from now on. Doesn't even have to be our moon anymore. There's so many good moons to go around. And it has this like long equatorial crack in it. And basically people think that whatever it started with was probably like a nice combination of rock and ice. And then as the rock and ice sort of started crushing, some of the ice lost its integrity and started to collapse. And so it's collapsing in the direction of the rotation pole. So what I mean by that is this is the equator here. And then this is straight up and down. It's like squishing down and creating this funny like walnut ring. Cool. Okay. Here's your Uranian system. We don't have a ton of really good photos here, but that's going to be what it's going to be. You have Miranda, Ariel, Umbriel, Titania, and Oberon, I think. These are relative sizes to one another. This one is my favorite one. This is Neptune's moon. I'm going to stop saying it. It's much more massive than the rest of Neptune's moon. I showed you Uranus moon. This is Neptune's moon. This is a little bit smaller than Europa. And we think it had to have been captured. And so remember we were talking about upcoming rings. So if you're ready, you just put yourself in a little time capsule. You wait 3.6 billion years and you get a brand new Neptunian ring. And this one's fun because it looks like cantaloupe. You might have seen this one before when we were going that big overview, but now we have a little bit more context. And of course, it has these little features. What are these features? These black ones? Yeah, cryovolcanoes. So those are cryovolcanoes on Titan. Pretty fun, right? Okay. Any more moons you want to talk about? Okay. I guess I'll see you in a week. Yeah, you want to do more moons? I can do more moons. That's all I have for this one. That's like 56 slides of moons. We can do more. Just give me 2 seconds. All right, everyone's leaving. You want more moons or no? Nah. All right. Here, I'll just I'll take separate questions. How about that? Oh, it's okay. All right. I'll drop it off. Thank you. Okay, anyone who has any space question, I have a slide for it. This one has 295 slides. Everything you want to see is already here. Oh, fuck. Why would you do that to me? Oh, yeah, yeah.
Take her back somewhere to see.
Okay.
Email you as soon as she can about.
Tell her, don't worry. I understand. I knew ahead of time. I'm not worried about it. Okay.
Hey, Dr. Lawrence.
I know, right? Oh, fine.
Is it
Yeah.
true that Mars had rings too?
I don't know if Mars did have rings. So, in order for Mars to have rings, it would have to have had an object that became the rings, right? And it no longer has an object of that size. Since we don't quite know how Mars got its 2 moons by now, it's quite tricky for us to know whether or not it had moons before it got, or had rings before it got the moons. That makes sense?
Okay. Oh, will it have rings in the future?